Now, let's take this as an example. I need to reproduce all these numbers. I'm thinking about, is this possible with just a single vector? Taking into account that I also need to be able to reproduce all these numbers. And so, and the one before that, and one before that. Probably not possible. I don't know. Could remember the 2 and the 3, then I have the +1 and that repeats. So I have this whole column. And then I can remember the 5. So I have the 3 and the 5, so I have the +2 and that repeats, so I have this whole column. And then I can remember the 11, and yes, these are all prime numbers, that's why I made a mistake, thinking that it would always be prime numbers. So now I have the last one I remembered was 5, so I still have to remember the 7 and the 11. And then I have the +4 as well. And then here you have to remember the, I know I have the +4, so I have to remember the 13 and the 17 and the 19 and the 23. And then we have all of these, but I still need to add 26, sorry, the +2, the +2, the +6, the +2 and the +6, and then it repeats. And there is 2 things in the middle here, that and that. Now the reason I find this 25 is because I'm just repeating these two. 24, 24, 24, 24, 24. So the first problem, the first problem being the square of 5, is after the repeat. And therefore I'm not storing it, and it doesn't give me a problem. So I'm just storing, again, just prime numbers. And now I have this whole list. And then here it goes wrong for the first time. Because now, I mean, the repeat, or same here, the repeat stops at 11 and 25 is larger. And this repeat stops at 37 and the 49 is larger. So this is still working. But in this column, the square of 11 is 121. And the repeat didn't finish yet. The repeat continues after that point. All the way up till 221. So eventually, hey Matthias, eventually these things grow Eventually this might repeat continues on and on and on and on. And they are different as well in the beginning. I'm just thinking out loud, otherwise I might as well not stream. So the thing is that there are so many numbers the same. Kind of stuck, I have to say. All these numbers are the same. Except here, and then there's a difference. Yeah, okay. Okay, well, I think I just did nonsense in the last 10 days, something like that. It's just not working. I would have to remember all these numbers, and then in every column. That's a vector per prime. That would use a little bit too much memory. Of course, there must be a way to compress it somehow, because there's a lot of overlap. There is a lot of overlap. But yeah. It's pretty easy to reconstruct this column from that one. But if you repeat it, at some point I have a column and I reconstruct that from the previous column, but that one was already reconstructed from the previous, and that was reconstructed from the previous, and that was reconstructed from the previous. And then eventually the thing gets horribly slow, because you're at prime 1000 and you have to reconstruct from columns that didn't exist yet 1000 times back before you have the actual number. Starts to look like trying to divide by every prime number there, to see if something is a prime. So no. Okay, I had something else. This. I don't know how much of a dead end this is. Probably also, but still. The idea is you begin with a hash. Let's see, theoretically this one starts with 7. So we're going to do it with the previous one. That would be 5. I don't know, 5. Let's put them here. 5. And then I add this one. These are numbers, and then comma modulo 7. So 49 is modulo 7 is 0, of course. And 127 modulo 7 is 1. It was me. So 5, now we do modulo 5. Okay, so this we start with 5, modulo 5. And then we do the next number that is not divisible by, all these numbers are not divisible by 2, 3 and 5. So now we do all numbers that are not divisible by 2 and 3 in this case, which means that we skipped 6, but the 7 is still there. Modulo 5 is 2. And then we have to skip the 9 because that's divisible by 3. So we get the 11, of course. Modulo 5 is 1. I think the width has to be 2 actually. So the 11 should already be on the next line. Yeah. And the height is gonna be 5. As you can see, the height here is 7. 1, 2, 3, 4, 5, 6, 7. Okay, plus 1. So the height here is going to be 5 plus 1 is 6. And vertically, we just add 6 every time as well. So I can just finish this column now. 17 plus 6, 23 plus 6, 29 plus 6 is 35. And then I have 6 of them. And if you add 6 every time, then the modulo 5, of course, it gets incremented by 1 every time, because 6 modulo 5 is 1. So I don't even have to think about it here. This is just, oops, that every time add 1 modulo 5. Same thing here. 7 plus 6 is 13. And 1 there, and this is plus 1. $19.4 plus 6 is 25. 5. Whoops, 5 is 0. And plus 6 is 31. Plus 6 is 37. So the plus 6 going down every time, plus 6, plus 6, plus 6, plus 6. The 6 is just 2 times 3. That's a thing that is not divisible. Each of these numbers these are just all the numbers starting at 5 that are not divisible by 2 and 3. Therefore, downwards we add that. And here we have all the numbers that are not divisible by 2, 3, and 5. And therefore, going down, we add every time 2 times 3 times 5 is 30. So each number here is going down is 30 more. And another structure that I'm built into this is that the modulos are the same horizontally. So you have 3, 3, 3, 3, etc. All the lines here are the same. And I want that to be the case here as well, which means that I have to shift it. You see already that this is nonsense. Well, it's kind of nonsense, yeah. Maybe I think the next one might shine a line on it that this is just a coincidence that you can do this. That's my feeling. Anyway, if I want these to line up, then I'll just have to 4, 3, 2. So it must go at the height of the 2. Oh. What happened? I removed that. Right. It should have worked. Delete this and then put it there. So going from 5 to 7, we added 2. Therefore, the modulo goes up 2. And in order then to line up with the ones here, which goes up 1, because 6 modulo 5 is 1, we have to go down 2. So the amount that we go down is, yeah, coincidence-ish. 7 minus 5 is just 2. It's just not that much of a coincidence, because it's the first, probably always 2. Although here we start with 17, of course. But if you start with 7, then the next one is, well, actually this one is 11, because plus 2 equals something that's divisible by 3. So yeah, let's call it a coincidence then. So we go down by 7 minus 5 divided by 6 modulo 5. And then they line up. And that doesn't tell us anything, because, well, it's just such a small table. Let me make it look the same as the one below there. Although this is probably, if I add this and kind of not really nice, because I'm doing it anyway. But the next number, if you want to repeat this, so we add 6 again, then the 41 doesn't come here, because then it doesn't line up anymore. 41 really has to go here. So 35 plus 6. But okay, maybe the plus still should be there, so you can see that 35 ends here. Or I could do this maybe. Something like this. Yeah, it's probably better. But it also only works if we still have a space left here, which is not the case here. Need some kind of ASCII, UTF-8 ASCII thing with a vertical bar here. I'm not going to do that. Anyway, I could try it with the next table and then call it a day, because I think it's a dead end anyway. Now I'm having here. Created that one anyway. Let's start with the 3. And then modular 3, of course, and then we have to just go down immediately. +2 modular 3, and that's it. There's only 2 of them. Well, I want to make 2 + 1, so I have to put the 7 here as well. 7 modular 3 is 4. And that is the end of the table. And then it repeats. All the numbers not divisible by 2. That's odd numbers, by the way. And that's a 0 again. And so on. Now note that these 2 things here, the 5 and the 7, are exactly the ones that we have here. So that's why also these numbers here are the ones that are not have a 0. So that's these, and then below the 7. So not the 0, so you can highlight them like that, but then not the 7 here. The 7 drops out as well. So you remove the top and you remove the 0 line. So everything above the 0 line, but not the 5 and the 7. And on here as well. Everything above this 0 line, which is just one element, and then not the 3. So the 5 and the 7 you put there, and then here you put the 11. Why am I starting with 7 here? I am starting with 7. Yeah, you have to start with the 7, that's true. I'm confused. Let me check. The lot is 131. I did it differently than before. So I'm rambling. Before I had this whole table written differently, I think. Yeah, well, okay. Anyway, I thought maybe it would tell me something if I shifted these things down. But if you don't shift them down, then you get a nicer block that you can point at and say, maybe you can do both. Let's make a copy of this. Let me put that here. And then we move this one up again. And the 41 was already an extra anyway. So the numbers, yeah, but I do start at 7. How the hell is that possible? So before I was just doing these numbers, 11 till 37, and but not the 25 and the 35, because they are divisible by 5. Which makes sense, because the next table has to table stuff that is not divisible by 2, not by 3, which are these, and not divisible by 5. Therefore, we just remove these 2, and then you have them left over. And because this number is divisible by this 2, there's a number, the width here is 8, so you just get a block of 2 by 4, which would be well, +2, but they are all separated. There is 1 0 in every column, so then you end up with 2 by 5, 2 wide and 5 deep, and the 5 deep is just simply this 5 here. So that would be this block here. But now I shifted it and I started at 7, and then rearranged the columns, by the way. But okay, I start with 7 and I end with 31. And before I started with 11 and I ended with 37. Maybe that still makes more sense actually. But if you apply that here, then I would, yeah, that would be correct, right? So just those two. That still works. I think I shifted it back in order to get my first column to end on a 0. Because you get here the modulo, I mean, it repeats if you go down. So if you start with something that is 0, modulo 5, then the last one is going to be the one that is 0 again. Not something in between. And I thought that would be nice. So I wanted that to have that here as well. So I started with Zev 7, so that the one at the bottom is 0. And then I shuffled the columns so that the 7 isn't even at the beginning anymore. Yeah. Nah, maybe I should have not done that. Maybe starting with 11 is better. That would be a whole rewrite. Maybe I should just write a program to generate these things. And then we can generate one more. And that then is going to be 48 wide. And 11 high, right? This one is 7 high. Or 12 high if you add the top row. 12 by 48. And I'm going to need probably 1, 2, 3, 4, 5, 6, 7 per column. 48 times 7. That's 336 characters. How many characters can I put here? Yep, that's 140 something, 144. So that's way more than fit on my monitor, unfortunately. I can make the font really small, and I have another monitor besides this, and then I maybe just make it. I could not show it to you guys. Do I want to do that? Write a little program to generate it. I'll also explain why I wanted to do this. Is actually I was just thinking ahead to the compressed Aristotle's Sieve, where you only store the numbers that are not divisible by the previous prime numbers. And then the question is, of course, how you can strike out numbers that are divisible by the higher prime numbers. For example, if you have the normal, the most basic sieve of Aristotle's, then you just list. I'm gonna even put it in that form. You just list all the numbers starting at 2. Well, actually that one goes up here, right? I mean, that's even above this one then. 2. Modulo 2, and then we get 3, modulo 2 is 1, and then we are done again. Let's see. No, again, this is the top line is just, you know, for bootstrapping. So really we have too wide and too high here, and I added this one for fun. I should add an thingy there as well. Well, actually, the shifting is bullshit anyway. Let me add a thing here. So this is the top row, and then the height here is just 5. 1, 2, 3, 4, 5. And then here I have, I should have 1, 2, 3, I think. Whoopsies, sorry, that's going there. And now this one is going to be too high. Okay, 4, 0, that's it. Is the one before this one? No, not really. Actually, there should be. We can add one more. It's a bit vague here, right? It's definitely vague. 3, I'm not too sure if this modular 1, but 1 is not a prime number, so. Should not be tempted to say, okay, everything is divisible by 1, therefore there is no other prime number. It's not a prime number, so the zeros are not really important here. And we don't drop anything out, so that's really, we don't have anything, and we just continue with the 2 here. I'm not happy though. This is modulo 2 too high. I should make it just 1 high, right? So, is that no nonsense? I know it repeats by 1, so I just drop out this one. Yeah, so the first one is a bit very flaky. Maybe we should just start here. So this, I'll copy it, is then the simplest sieve. Put it all the way down here. And I stopped, but really it does continue. It just repeats after this. So we'll type a few of these things. Repeat. No, one more. And so on. So these are just all the integers, and what we do is we mark the ones that are divisible by 2 by writing a 0 behind them. So this one is a 0, and this one is a 0, and this one is a 0, and that means that they are not prime. And therefore the next prime that we find is the 3. And then we write down, I could, all this now the modulo. That does not mean that this is not a prime number, but okay, let me just remove it. So 3 is the next prime number, so we add 3, 1, 2, 3, and then we add a 1 here. 0, sorry, it already has a 0, but I'm writing the 0 here anyway. And then we have 1, 2, 3, so we add a 0 here. 1, 2, 3, add a 0 here. and so on. So that marks then that the 6 and the 9 and the 12 are divisible by 3, so they are not prime. And then we find the next prime to be, well, not this one because it has a 0, but this one, this is the 5. So we go 5 down, 1, 2, 3, 4, 5, and run a 0 here, and then 1, 2, 3, 4, 5, and add a 0 there. That would be the 15, of course. And you do that all the way up till a million, and then the ones that are left with no zeros in it are primes. And you can compress that, and that is pretty usable, which actually means that you start with this table, just the odd numbers. So now we already removed all the even numbers. 11, 13, 15, 17, 19, 21. I'm afraid you have to continue quite a lot before you see the pattern. So I'm going all the way till no, don't feel like going further. To the only thing that matters here are the zeros. So I can write down, of course, the modulo 3. So then this is again a 2, of course, because like I said, it repeats. So this is 2, 4, 0 again. And then we get here again 2, 4, 0. And 2, 4, 0. In other words, every 3, if you go 3 down from the 0, 1, 2, 3, then you find another one that's divisible by 3. 1, 2, 3, that one is divisible by 3, and so on. And then the next prime that you find is 5. So if now here I write down the modulo 5, then of course 5 modulo 5 is 0. And then we can go down just 5. 1, 2, 3, 4, 5. And that is divisible by 5. 1, 2, 3, 4, 5. That's divisible by 5. And so on. And then you see that the one that is left without zeros is the 7. So the 7 is the next one then. 1, 2, 3, 4, 5. Oh, that doesn't work. A 7. So you have to go down 7 now. 7. 21 is divisible by 7, and so on. So that's how the Sieve Eratosthenes works. Usually, and then you have it compressed it. Yeah, the table length is now the half of what it was in this case, because of course it's kind of silly to store all the even numbers and then immediately skip them. But hey, you can do the same thing with the 3s. Just remove everything that is divisible by 3. And now, of course, it totally works if we would do that like 5. Blah. So we're going to repeat all the numbers that are not divisible by 2 and not divisible by 3. So here we get the 11. So just going down here and then all the numbers that do not have a 0 in this column. That is 13 and 17, 19, 21 skip, 23, 25, skip 27. So the next one is 29, 31. Then we skip 33. No, I'm missing something here. Definitely skip 33. But the 35? No, 35 is still here. It's not divisible by 3. Skip 39, 41. And then we say, okay, now we begin with the 5. You can still go 5 down, right? 1, 2, 3, 4, 5. No, it doesn't work. So here it did work. You could still, because removing all the even numbers didn't change the distance between things. But now we are skipping 2 from 5 to 7, and then we skip 4, and then 2, and then 4, and then 2, and then 4. So it doesn't work anymore. You cannot easily say, well, okay, the 5, and I want to find the next thing that's divisible by 5, which is the 25. So you go 5 down, like you did here. You go 3 down, 1, 2, 3, and you have the next one. 1, 2, 3, and you have the next one. But if you try that here, 1, 2, 3, 4, 5, nope, you have to go 2 more. Okay, so maybe it's 1, 2, 3, 4, 5, 6, 7 for some reason. 1, 2, 3, 4, 5. Yeah, but then you skip the 35, so it just doesn't work like that. I am live, yes. The vital. I have 5 minutes. What is the problem then? While you type your question, I'll continue here. So in order to get the distances downwards again equal, you just have to put everything. Oh, that doesn't work. You have to put this whole thing in a table that is too wide. I'm gonna put thingy there. No, I'm not. Yeah, same numbers, but now written in a table that goes, that is too wide. And lo and behold, 1, 2, 3, 4, 5, it's a 35. Well, except here we have to do some more effort, because to find the 25 here, not as easy. But once we have it, we can go down 1, 2, 3, 4, 5, and then we have the next one. And all these numbers have a distance of 6. So this one is 47, and this one is plus 6, 53. Same thing here, plus 6. And plus 6 is 55. So yeah, once you have the 25, you can just go 1, 2, 3, 4, 5, and you have the 55. So if you make 2 tables, in this case, then you only have to find the 25, which is calculatable. And then after that, you just do plus 5, plus 5, plus 5, and you mark the table as what is divisible by 5. However, the next step is crossing out everything that is divisible by 7. How do we do that? So that doesn't work either anymore. The 7 is here. 1, 2, 3, 4, 5, 6, 7. Oh, that worked. And this is on, in this table here, this is on the first one that is divisible by 7. What if we go 7 down? Is that the next one? Let me see. You have to fill in more. Plus 6, 59. Plus 6 is 61. Plus 6 is 65. Plus 6 is 67. Plus 6 is 71. Plus 6 is 73. Plus 6 is 77. Plus 6 is 79. And so on. Let me read what Divitel said. Really simple code. Can you look at it for me, please? Oh, there's a problem. You cannot paste links. I don't see your link. Uh-oh. You have to type it in a way that YouTube will not recognize it as a link. Show you in case your IQ is lower than 80. No link. See? No link. Got it? Try to give me the link without typing a link. Yeah, Discord, I guess. I could invite you to my Discord. Discord. Oh, someone else is asking me for a Discord link as well. So I'll have to do that later. But invite people. Copy. Right. Bright white. So this is Divital's link. And then he wrote, I have a file named sticks_descent_main.cpp. Yeah, I found it. Can you take a look at that file for me real quick? Have you disabled link sharing? Yeah, you mean I can turn that on? I don't think so. Do we have somewhere where I can post link? Okay, the rest. Well, what's the question then? Just this whole thing and I have to look at it without knowing what I look for? This is so not a 5-minute question, if I see this. That's, there I am you. And you think I see immediately what the problem is. So what am I looking for then? I'm not an expert in DRMU at all. I just got it to work once, which I forgot again in the meantime. I'm more like a prime number guy now. In this file, section 3 is not showing up on my screen, he says. Take a quick look at the function section 3 for me, please. Section 3, here. I'm not into this anymore, really, seriously. And I'm like, what? I'm not even using this library, which looks like a C++ wrapper around IMG stuff. Now, I would say you call this. What happens if you don't call section 1? Do you see it then? So if you in main comment this one out. You seem to be suggesting that these two are symmetrical. So if you comment this one out and you only do this one. But for the rest, I'm not into IMG at all at the moment. It would take an hour for me to get into it, not 5 minutes. Yeah, well, okay. So I would say you call this then if you wanted to be 5 minutes and you calling IMG end. That's not the best thing to do then, I think. So try commenting out this and this and putting that below these calls here to IMG end here. But now I'm continuing with my own code because 5 minutes are over. If you had a question about, say, libc wd or something, code that I wrote, but I don't even use that library. And I used it, I think the C version maybe, I don't know. I used it once. I'm not an expert at that field at all. So back to the primes then. So I have here. So we want to try to find all the numbers that are visible by 7. And at least this one, 1, 2, 3, 4, 5, 6, 7, seems to work. And then here we have this one, 1, 2, 3, 4, 5, 6, 7. So that seems to work, right? Can we reason why that works? Yes, because if this one is divisible by 7, and every time we add something that is equal to 2 times 3 times 5, then this one is definitely not divisible by 7, right? So we are at some number n, which is a plus b times 7. No, no, it's divisible by, sorry, it's just 8 times 7. So this one, 35, is 5 times 7. And then we add, so now we have 8 times 7 plus 2 times 3 times 5. That's a 41. No, sorry, that's the other one. We just add 6. Da da da. To make a difference, I guess. Because this number is definitely not divisible by 7. And therefore, the result, what we get, is a coprime of 7. Okay, not divisible by 7. I mean, is this whole thing divisible by 7? No, I try to divide it by 7, then you get an A here. And you get something that's definitely not divisible by 7, divided by 7 is not an integer. So the whole thing is not divisible by 7. And then the next number is almost the same reasoning. 8 times 7 plus 2 times 2 times 3. Also not divisible by 7. And then we get 8 times 7 plus 3 times 2 times 3 is also not divisible by 7. So this is divisible by 7, and 2 times 3 is not divisible by 7. So as long as this column is not divisible by 7, the whole number is not going to be divisible by 7. And therefore it is not going to be divisible by 7 until we reach 7 here. Well, then it is going to be divisible by 7, because then of course we can divide this by 7 and we can divide this term by 7. And that's the 77. And that holds for any prime number. Because if you replace, say, the 7 by a 5, that works still. Then that one is going to be divisible by 5. Or if you put an 11 here, this is not divisible by 11 either. None of these numbers are divisible by 11, because 11 is a prime number and these things are less than 11. I mean, it doesn't even matter that it is prime number, I think, but okay, it is going to be a prime number. So that works, yay. So I would say, yeah, I can put them all in. I can just make 2 columns, and then I just add the new prime number. Skip, 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 skip. And then here as well, skip, 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 skip. And then in the end, we can put them into a single table, of course, anyway. And then we have to skip the width times the prime number. So then we have to skip 14 down. We go, if you do 7, it's 14 down. Or if you do the 5, you go 10 down and every down. And then if you want to compress it even more, you get this table. I really have to do that table in a better way. So now we start at if you follow this reasoning, we have to start with 7. I think it's even less work to just copy this and then change it back into what it was. So I need to move this up. Delete, paste. Delete, paste. delete paste. Can I do a dollar here? Probably delete paste, Control V, down, dollar, delete paste. Delete all of these things. And I want my column, my 7 column as being the first one. So let's delete this. Put that here. And now we get the 11. And then we get the 13. 17, 19, 20, that's done. So we are back, okay. So this should work the same way, right? I mean, I don't think I need my modulars anymore here either. Let's remove these. I should have gone down one more. Right. Well, it's just exactly the same story. Pick some random number and then, for example, this one, and then we go 11 down. 1, 2, 3, 4, 5, 6, 7. Whoops. 8. But every time we add 30, so yeah, 2, 5, 1, 2, 8, 1, 3. What did it say? 30, 1, 1. It's already enough. Hey, that looks divisible by 11. So there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. So of course it's only going to be divisible by 11 if you add 11 times something that's not divisible by 11. And 30 is definitely not divisible by 11. So that's 2 times 3 times 5. And that holds for every number. So you have to find the ones that are in this table separately, that are divisible by whatever number you want, and then you can go down in steps of that number multiplied by the width, and the width of this thing is 8. So if you put all the numbers in one table, then you have to go down 88, of course, if you want to strike out everything that is divisible by 11. Then the question is now, how do I find all numbers that are divisible by the next prime? So, for example, we find all those primes, like, so most of these things are already primes. The first one that's not is the 49. So suppose you find the 13 or the 17 or whatever, let's say 13. Then how do we find all other numbers in each column that is divisible by 13. And now these tables are going to get really big really fast, so we do not want to try. We do not want to run over is this divisible by 13? Is that available? Is that available? No, we don't want to do that. We want to go straight to the right field. So, and then we have to find them in every column. So we start with finding what is divisible by 13 in this column. And in order to get a picture of that, I think I want to have a much longer table. So there is actually a number that is divisible by 13. So I'm going to write a program that writes out this table. It's 8 wide instead of 48 wide, so that's still doable. Let's call that table 2, whatever. CXX GPP. Include IO stream int main. And let's say we go. Did it work, by the way? Divital. If you remove that IMG end. I mean, you have to move it outside after the last one, so that you call it only once, I think. And I'm still curious, of course, to know if then it worked. The first row, I'm not going to write it without adding the semicolon. This is my first row. Substitute the bar with a comma globally. It should be 8 numbers, they are. And I'm going to do 0 till let's call this R of row. The row, how many rows do we do? Let's say 20. And then I'm going to print yeah, well, the whole array. Let's call that N. First row. We want to set a width of God knows what. I should know that from my head, of course. My width is 3. Oh, okay. No, I might get 1,000, you know, no, not really. I don't think so. Anyway, I can change the width later on. Let's start with 3. Is that right aligned by default? Do the set fill spaces. I don't even know if that is the case normally already by default, but well. And I'm going to print fr plus something, so I have an offset plus the first row, so that's n. That should do the trick. And then offset is incremented every time with 30. And I want a new line at that point. In case I debug, I flush it here, otherwise I could of course use just backslash n. Oh, okay, I'm missing all kinds of stuff. Array and IO, manip. And then I should have put a thingy here in between. I think that's about it. So now I wanted to find the first number in this column that is divisible by 13. Okay, let's call myself lazy. I'm going to also put a space in front of it. Oh, damn it. Let's first that, and then that. And then if something, put a space in front of it, and otherwise put an exclamation mark in front of it. Maybe the other way around. And then the number we're talking about is offset plus n. Okay, keep my parentheses anyway. Percentage, let's take 13 as a case. So if that's divisible by 13, we print an exclamation mark. Okay, that's trust in the computer. This is divisible by 13. I would definitely not have bet my life on that. In fact, oh, I'm typing the wrong thing. 247 divided by 13. 19. Yeah, of course. Clearly 19 times 13. Yes. So how can we find this one? Immediately. Like we are here and jump. We know it. A jump meaning I need to know this offset. Let's call this 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. What formula is going to give me 8? And then here we want to get 7. And here we want to get 0. And here we want to get whatever that is. I want to get the first one in this column. I guess we are working modulo 13 here then. So let's start with replacing every number by modulo 13, because I'm totally not interested in anything else than modulo 13, right? So just we're going to print modulo 13 value. And now I think about it, let's print the column number in front of it, or the row number rather, because that's the one that I want to find. Oh no, wait a minute, oh, don't look at this. Row standard set width 2. So we want to find the 8, because this is divisible by 13, which means that the modulo is 0, obviously. Now I would say that what we know is that the actual number here that we have is 7. Modulo 13 is, well, 7. So that's this 7. And every time we go down, we add 30. We know that because that 30 is 2 times 3 times 5, which is totally constant. For the compressed Eratosthenes thing, we just pick a prime, in this case 7, and then the 30 is just constant of the program. So I do have to calculate 30 mod 13, which is, I'm doing division here, 30 mod, I don't have a mod on my calculator. That's why I did a division. 30 divided by 13 minus 2 times 13 is 4. So you see the modulo, we know that 30, which is the constant, or mod, whatever we picked here, we pick 30 now at this point, is 4. So you know that every time we go down, we add 4. Yeah, 7 plus 4 is 11, plus 4 is 15, minus 13 is 2, plus 4 is 6, plus 4 is 10, plus 4 is 14, minus 13 is 1, plus 4 is 5, plus 4 is 9, plus 4 is 13, minus 13 is 0. Thus, we have to divide something by 4 to know the distance. And 13, modulo 13, 13 being a prime, is a field. So we can just do calculations in the field. How do I get 8 by dividing by 4? Well, that would be 4 times 8 is 32, and then of course modulo 13 minus 13 is 6. How do I get my 6 then? Is that 13 minus 7 maybe? Yes, of course. Okay, so we do 13 minus 7 divided by 4. All modulo 13. That should be 18. Only remaining problem is that C++ does not have a built-in modulo calculation. How do we divide in Z in? I should know that. Multiply by the inverse? Yeah, so I only have to calculate the inverse of 4. And then I can just multiply by that. What is the inverse of 4? The inverse of 4 is that number that when multiplied by 4 gives us 1. So the question is 4 times what equals 13 times some number plus 1. And I'm afraid you have to use the Chinese remainder algorithm for that. But okay, that is an existing algorithm. Let's do this one by hand, manually. What goes here so that this is true? 1, 2, 3, 4, 5, 6. Oh. Still not. 7. I don't fucking see it. Let's just do all of them. No. So 4 times 0 is no. Well, let's calculate it. Is 0. 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12. 4 times 4 is 16, but we want to work modulo 13, so that would be 3. 4 times 5 is 7. 4 times 6 is 11. I just have to add 4 every time, of course. 4 times 7 is 15. Minus 13 is 2. 4 times 8. 2 plus 4 is 6. 4 times 9. 10. See, that's why I couldn't find it. Just way, way, way far away. That's 1, finally. So 10 is the inverse of 4. So back to my original problem. So 13 minus 7 is 6. 6 times 10 is, well, 60. But then minus 60 mod 13 is 60 mod 13. I bet that's going to be 8, but... So... divide by 13 is that, minus 4 is that, times 13 is 8. Ah, unbelievable. It still feels slow that I have to calculate the inverse of 4. No, it's not slow. That 4 that was is modulo 30 mod the 30, which was a constant, mod 13. Oh, but I have to calculate it every time. I mean the 13 changes. So to recap, I wish I had a calculator that just could do modulos, but okay. Online modulo arithmetic calculator, does it exist? Yep. Online modulo calculator, cool. That's not exactly what I wanted. It's a mod B, okay. 13. Yeah, that is not hardly a calculator. Modulo calculator. Also not. No. What a stupidity is this? No, but I just want to calculate in Zn. And the only thing they give me is something that does a modulo. Ah, there we are. This is what I was looking for. Very good. So it's already on 13. So I wanted to say 37. We did 13 minus 7. Hopefully that works. Just minus 7 though. So minus 7 and then divided by 4. Is that not it? Let me think. Yeah, calculate 8. Yep, very good. So here we have, this one is 11. Yep, so minus 11 divided by 4. 7. So 0, 1, 2, 3, 4, 5, 6, 7. Yay. And then this one should give 12. So minus 4, yeah, of course. Minus 4 divided by 4 is minus 1, which is 12. 12. And here we have, this one should give 5, so minus 6 divided by 4. It's 5. Totally works. And now the 4 is, I mean, this is just a negative number of what is it, what we try to, wait a minute, but it's actually, yeah. Let's see if I can just fill in this number. So of course I should be able to. Yeah, of course I can. So is that 29? Does that work? 29 divided by 4. I might as well replace the 4 with what it really is, namely, wasn't it like the 30? It's 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 299 divided by 13 is 23. Yeah, that works. So we just take the negative number of what we have and then we divide it by our constant. But we have to do that modulo the one that we want to find, that it is divisible by. For example, what is the first number in this column that is divisible by? Well, 29, for example. Then we do minus 19 divided by 30 modulo 29. And that's 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is divisible by 29. 3, 1, 9 divisible by 29 is 11. Yes, it is divisible by 29. Works like a charm. And now the only thing I'm worried about is what happens if I just go past that point. Like now I'm going to try to find the first number that's divisible by 73 in this column. So minus 23 divided by 30 modulo 73. This column, 73. Minus 23, 73. 26. No, that's correct. 26 is the answer. So the first number that is divisible by 73 in this column is that one, which is at position 26. So what we're going to need is a modulo calculator in order to find that. Where the modulo rapidly changes. But so what it does is it forgets the minus. It just says 23 mod 73. Well, that's just 73, of course. I could do this in C++. And then the negative means that you subtract it from 73. 73 minus 23 is 50. And we do the modulo 73 is also simple, and then we do the inverse. Bang. And nobody knows how to figure that one out. Yeah. That looks it. How to calculate the inverse of 30. You think ChatGPT knows this? No. Okay. I finally did this correctly. So you can tell it in the settings. Already here. You can add custom instructions. And in my custom instructions, I have it's like 1,000 characters at most, I think. I have, among other things, written that it has to write comments that are English sentences, like they start with a uppercase and they end with a dot. And that's what I'm doing now. Otherwise, I would not have done that. So it makes me happy. Also say that after every keyword, it must use a space. So here, and I have I think the demand that it put const on the right of types, but there are no consts in here. Let's see if we can use this. So let's calculate in advance when this is the case. So at this point, we're writing the exclamation mark, and I want to assert here that we have predicted the correct value for a row. So that's PR predicted R equals R, and then we have to predict R as a function of printing this left to right. You have to recalculate it every time, I think. So PR then is yeah, it could be larger as well. Let me check this. What I really want is that PR minus R modulo M equals 0. And then the PR can be calculated as minus current value. So just the first one there. Row, I don't know. No, I have to calculate even here. And we have to, I can calculate it from N. And it's just this number at the top. So I want to calculate minus N divided by 30. Modulo M, right? That was the trick. And we're going to replace that with multiplying it with the inverse. Let's call that the vertical offset inverse. I'm going to call this int const vertical offset is 30. And it's always the case, so yeah, all of these numbers are less than the prime number, so the GCD is never going to be unequal 1. So we can skip that part. So I'm just going to do mod inverse where did my n come from? I called it m here, and it's called n up there. Well, okay, I'll call it m here. Maybe I should call it n as well then. And I need my insert header. Well, that worked. Perfect. I mean, it doesn't assert. Every time we did print an exclamation mark, we have just tested this assert, which means that we predicted it correctly. Ain't that awesome? Okay, let's see how we can turn this into a prime generator then. Yeah, I think it's fast enough. I don't know. I was thinking maybe I can speed up calculation of that inverse by using the previous one. So let's look at these numbers. So we did calculate the inverse of 30 for this one, and then the question is it not easy to speed up calculating the inverse of 19, already knowing the inverse of 17? Not really, is it? I don't think so. Yeah, it just looks kind of random how these two things are, you know, the hashtags and the exclamation mark, they're all over the place, but well, they have regular distances like this, but there's hardly a relationship between the exclamation mark and the hashtags, I would think. I think it's time to start over with fast prime 7. I mean, in the end I want to write something that is reusable code for generating small primes. Let's make this one like that too, though. So namespace debug init, right? So I have to peek anyway. Peek at this. Namespace debug is it? It is. Right, and then we're going to need table 2 code. Let's copy this. Okay, what API do we want? I still need to have my prime number type. Is it possible that these things will become negative? I mean, it seems it's very suggestive here. And there is a subtraction here, but... Yeah, while b is larger than 0, maybe it becomes exactly 0. A becomes b and b becomes a mod b. A was positive, pretty sure, initialize. A is positive, b is definitely positive. Positive, well, not negative anyway. Everything is not negative. Therefore, this is not negative, and then a becomes b and b becomes a mod b. That is also not negative. X0 becomes x1, so also not negative, and x1 becomes that. So that might be negative, but is it? I don't think so. I'm confused. Yeah, okay, I'll believe it. ChatGPT in calculation makes me very suspicious. But that means that I have to use assigned integers here. Or at the very least, assigned integers here, which then in turn means, I think, I'll use unsigned integers here. If I use unsigned, just for the sake of being able to use very large numbers, that means then, because I assign it to b, that n and b, I guess, have to be... No, this is always 30, so I don't care about that one. Then b must be unsigned. And b becomes a... So if a... Well, I could make it unsigned if we keep this positive. But that's a problem. I could then... I would have it add a test here. I don't like it. Let's make it signed. I guess... Man, that really sucks. Prime type signed. Doesn't feel like the right thing, right? Let's add a comment instead. Wait a minute. No. I'm going to use 32. And in that case, it doesn't hold anyway. Let's just use signed for integer then. Or maybe I just want to do something as long as possible. Sorry, as big as possible. So long. I'm not convinced. It's a... I don't know. Not even sure about that one. It might actually be enough to just use yeah, I'm going to use 2 integers, I think. So much for the types. Chi, so I'm going to have a vector, I guess, of prime types. Be returned by a function And I pass the number of primes, or just the largest value. I think the largest value. So that has to be an integer then. A large number. Okay, we need a few primes as bootstrap, so let's just put them in an array. I don't know what type. Well, prime type or not. I don't know how many though. Not that many. 8. I don't know. Maybe more. I'm gonna go all the way. Well, why not 16 then? Because who cares? It can only be enough, right? So I'm at 8 there. 23, 29, 31, 37, 41, 43, 47, 53. I have 16 already. 8. Yeah, that looks like 16. Hmm. What is a good... Okay, of course, primordial. Yeah, for example, if we use compression of 3, so 2, 3, and 5 are being skipped, then we have this table. We start at 7. Because, well, we don't even know anything about 2, 3, and 5. They're not in my table. Therefore, the first 3 primes have to be I just copied. So we started copying that. That's this line. Next, next we need a huge thing that is basically representing all the other numbers. And I need to calculate how big that is then. So calculate how many integers are not divisible by the compressed primes. That's those primes. I don't know, compressed is a bit weird, but you have to give them a name, right? Okay, let's say by the first compression number of primes. That are less than or equal max value. That's probably going to be an integer. No. Or is it? Well, whatever. No. Is it? I don't know what size it is. Before I was calculating the square of primes, but I'm not going to do that now. So maybe I can make everything like 64 bits, which is ridiculous. Do I ever want to calculate more primes that are larger than 32 bits? How big is that? Oh, is that 32 bits? I think so. yeah, maybe not large enough. I mean, it would be fun to go to the square of a million or something. So it's actually a little bit larger. That's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah, this is the number I would like to use, which is then 40 bits. Okay, so 32 bits is maybe it's not enough. Might as well then work with 64 bits. Larger than 64 bits is ridiculous. So long is nah. It's just restricted to 64. And then this one, yeah, could become larger. I'm gonna make this unsigned though. It's kind of stupid to call a max values is not per se a prime, but it is in the same range as the primes, which is now reflected just purely by the fact that they're both 64 bits. And you would say, yeah, why would I accept a negative value for the maximum value? But that's not the point. I need that here. I don't want to introduce yet another value that is unsigned, but not a prime. So, well, whatever. Or maybe I should do that. I don't know, man. Integer, unsigned integer. What is a good name for a big integer that is only going to appear here? I think I'm happy with integer. Or I could make it just prime type, I guess. Would just look silly. Maybe you can just fill in uint64 type here. So that uint. Not a, it's kind of like the only place where I need it, and that is the same as prime type, but this is not a prime, so I don't want to use prime type. Previously I called this the repeat. Let's add another const. I could make this a template thing. To a const expression recursive function that calculates this from that. If I make this a const expression, maybe a const expression function. Why not actually? Let's do that. See if that works. An array can be const expression. And then we can make a const expression function called primorial. Which of course I'm going to steal because I don't want to think about that again. Hello. Primordial. Bop, 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 bop. There it is. Yeah, can't even get a comment. Copy. Because Y better. Next. P. Oh, that didn't work. Oh, I selected it with my mouse. Shift V. Y. Next. P. Make it const expression. It's no longer part of primes. Oh, this thing needs a prime index. Oh, why not? Okay, so then this P becomes small primes. Guess. Oh no, I copied repeat. What the fuck? Probably a member, a class member, but well, let's put calc in front of it. So now we can make this zip, a primordial. Calculate the primordial of compression. Does that work? If we pass 3 here, then we do set lesson. No, so we return small prime 3, 0, 1, 2, 3. So that does not work because I want to go up till 5. Yeah, usually I had it, so I have to just subtract 1, I guess. So now we get 3 minus 1 is 2, 0, 1, 2, that's 5 times the thing 1 less. So the next time we get 3 times that, and then we get 2 times that, and then this was 2, so this was 2, so this was 0. So we calculate the thing with 0. And when it is 0, it's less than 1, and then we return 1, so that works. And I repeat. Then it's a prime index type. Why on earth would I call that a prime index type? It's also an integer. But on the other hand, I want to use an int maybe. I don't think my repeats or primordials are ever large. They shouldn't be. I think it's gonna fit in an int. Just use int. Which means that my prime index type should be an int. Then everything works out just fine. And here we have calc repeat. Compression. Now I want this to be 8, so that's indeed just those 3 multiplied but subtracting 1 every time. Yeah, so this becomes 2 times 3 times 5 is 30, and this becomes 1 times 2 times 4 is 8. In this case, unless, and if I make that another number, then it changes. And then of course we want to make sure that this is the case, so let's print it out. Compression is compression. Compression primordial is compression primordial. And compression repeat is compression repeat. Now it's time to try to compile it, I think. Which won't work because I better now make a CM thing for it. This one. Cannot have non-literal type. What? What's non-literal about that? It just means that I didn't include array. Really? What do you mean non-literal? Cannot have const qualifier. Forgot to remove that one. Return expected unqualified ID. Missing semicolon? Yeah. Junk in the middle. Not compiled. And now the question is, do we have fast prime 7? Nope, we don't. PE. Maybe I just have to resource it. This should do it. Let me try the resource. Now I have it. Yes. And as you can see, the compression repeat is wrong. Oops. Yeah, this repeat for some reason goes till -1. Maybe I should get rid of that then, because I don't need it here. No, it's not true. That is PK. It just goes to PK. It should go to PN. Oh, it's again the shift in the small primes, I think. Yeah, probably. No, it's not. What the hell? Seems that this 3 is not good for some reason, but like I say here, it's the same thing as the other one, except that we subtract 1. So now I added a -1 here. This one automatically becomes correctly the same thing. But then you would say this now has to become 2 probably. Less than 2, it's 1. Yeah, I think that's correct. As in not 1, but including the 2, because 2 minus 1 is 1, and multiplying by 1 doesn't do anything. So you might as well stop here. And now it's 8. And I still have to calculate this. So how many of those things are there? Well, if we go to, let's say, and this table belongs to compression of 3. And that means that every 30 we have 8. Let me think. I think it's not a bad approach to start with the number of rows. So I have to start with dividing it by 30. For example, let's say our number is 121. Then yeah, I have subtract 7. So if you take this one example, that is on the edge. 127 minus 7 is 120, which is 120 because it is 4 times 30, where the 4 is these 4 rows. So 126 should still give me 4. Which means that I need one more than this minus 7 divided by 30. Yeah. That means I need that one as well. So I need the first prime. Let's just call that the first prime. Hello. So in the case of a compression of 3, we skip 3 primes, and then the first prime is 7. So it's not really the first prime, so we might as well call it a compression first prime maybe. Otherwise it's confusing. And it doesn't have to be big, I'm just going to make it an int. All those compression things. Zero, 1, 2, 3. Yep. Now, of course, you have to check that by just calling it for a lot of times. For int max value is, well, let's not be nasty, and at least start at 100 or something like that. M is less than, I don't know, 200 to do it. Let's not print anything. Wait, I want to actually also print n itself. Something went very wrong, I'm pretty sure of that, because array size is 4 in all cases. What the heck? Oh, because I passed 100 instead of m. Tick. Well, let's say we have a look at it. 100. I think I added this and I see my table. I want to print a table again. Let me see. I think I have a G++ table. That doesn't print very nice. It's not very nice. I want to see my actual values, I have to admit. It does not print a modular. So 100 requires this, which means 1, 2, 3, 4. That's correct. And that remains the case until 127. That's here, yep, because as soon as you want to include 127, you need 5 lines. And then we remain at 5 until exactly this value. That's 157. Yep. And then the next one is 187. Requires 7. Yep. Pretty good. I'm convinced. It worked. Oh. So now we have the total number of rows. It's not the array size actually, it's the array rows. The required array rows. The total array size is slightly larger. We want to do it exactly. And why not? But I'm thinking that maybe I should just allocate the whole row. Might in the end speed things up. Yeah. Let's just calculate allocate the complete rows. So Yeah, and then of course we can go like bits, but that makes things extra complicated. For now, I think I'm just going for characters, for bytes. And I will just use a vector, I think. Oh, character of byte. Let's call it a byte. I think I have a standard byte type these days. Shall I call it a char? Well, let's call it a char. I could even call it a bool, but then, yeah. I'll have to test if that slows things much down. Probably does. I mean, vector bool is specialized, and then it's going to do all kinds of difficult shifts and stuff internally, which we probably want to avoid. I'm gonna go for char at the moment. That's my array. Actually, let's call it a sieve, because that's what it is, right? So instead of array, sieve. And then the size is the sieve size. You can just pass that to vector. And we have to fill it with something. I think by default now it's filled with nothing because I made it. Yeah, it's default. It's filled with default allocated chars now, which is just 0. I can fill it with something else. I think it's much faster if I use memset, however. And I hope that this one is cleared already with memset and not one by one, if you get what I mean. Maybe I should use malloc here. Not sure how slow this vector is going to be. I should, I guess, test it, you know. Allocate a vector of 1 gigabyte or do a single malloc call for 1 gigabyte and see which is slower or faster. But I'm lazy. I think I'm lazy. Hold on. I'm just going to use malloc, I think, just in case. Well, I can use new. I mean, doesn't really matter, I guess. Well, new is going to do the allocation again, doing the theoretically is going to do the construction again. So it might. I'm gonna use malloc. I want to know what's going on here. So that's character pointer. Do we have a standard malloc? Or is it just malloc? Let's have a look. You have a standard malloc. Then I'm allowed to use it because it's standard. I say. Now at the end we are done with that. So you can do standard free Sieve. And of course you have to fill it with something. Let's fill it with ones or something like that. So we do a standard mem set of the whole Sieve with 1. That's per byte. Mem set fills per byte, right? Yeah. Okay. That, of course, is going to be 0. Okay. I'm going to have to calculate back from the index of my sieve to the actual prime number. Is there a faster way to do this, or is it not the slowest part? I'm gonna have to do this for every prime. It feels pretty slow. No, let's start with this. Okay, so index is now just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, and so on. And then we want to know the prime number. So that is obviously, if we know the 10, then we know that it is 7 plus 10 times 30 is 307. And then I need to know the offset from here to there, which is probably best to just make a table for that. In this case 10. And that 10 I find then from the offset from here to there, so 1, 2, 3. So I have a table of 3 points to 10. And the 3 I get from the fact that the index minus the index, it belongs to this one, which is simply that one divided by 30 times 30. That's annoying, but okay. All in all, I'm going to have to do a division. That's nonsense. Yeah, nonsense, nonsense. This should be the repeat. And then we return the row times the compression primordial plus some table. Well, that's just a prime number. That is just a prime number, isn't it? Something. No, it's not the prime number. It's the whole first row. Gonna have to just call it first row then. First row plus, let's call it first row offset. Or I have to remove the first prime. And the index then of this is column, of course. An array. Now these are pretty small things, but we are calculating with row times compression primordial. Oh, that is an int. A row is an integer. Why? Is that really necessary? Yeah, probably. So this is already an integer, and it doesn't really matter what this is then. Int fits. I'm gonna make it an int. Who cares? Repeat. So I need the first repeat numbers, which we can also calculate in. Calculate first row offset. I bet I want to pass compression here. So that would be a constant expression function that returns an int, and whose name is that, and it takes an int. Why am I even passing compression here? Oh, because I could have moved it upwards here, up here, but well, nah. I think I have to do something else. I mean, it must be recursive, right? So I want to know which number. Let's say the column and the current prime, which is what is going to be returned. And the compression number then. But we already know that because you can just use compression because this thing is below that. So maybe I should just do that. And then this is calculated the whole row. It's an whole integer, it's an whole array. This doesn't return an array. Let's call this offsets with an S. And we're talking about offsets, the offset relative to the first column. So if column is 0, then the offset must be 0 because we are already in the first column. In other words, the first one must be 0. And then I is just a column, so let's keep using the same names here. Call. I'm going to call that. So that's going to calculate the offset relative to the column. I'm kind of confused how to do this. I don't think I need a thing at the top. Might as well do everything here. So I'm having a first prime. It's the current becomes current prime. It's the first prime. Even that is not. I just want to start at 0. candidate is going to run over all integers, and then when it is what I want, I'm going to assign it to the next column, an increment column, at which point we have call number of columns. So if that becomes equal to the compression repeat, then we're done. And then this loop is going to increment candidate with 2 because I don't want to waste time on the even numbers. Now we should do this only when it is not divisible by any of the other compression primes. So pool is divisible by any of the compression primes. Test that. If not is divisible, add it. And the test then is that we loop over all the first compression primes. Let's use n. N less than compression, I guess. No, let's not use n. Let's use I. It's a bit confusing. So Pn is like the nth prime, which worked wonders for me when the array had 2 in index 1. First prime is 2. But now I'm like, yeah, I started 2. So let's call it I of index. If something then break and is divisible, it's true. Well, the number of compression primes is so small that it might as well test everything. But no. If candidate modular small primes I equals 0, then it is divisible. So now I'm trying to divide it by 2, which is nonsense, so we start at 1. Started to try to divide it by 3, if that is then it's divisible, and I'm trying to divide it by I is 2, which is 5, and then if etc. And it's not divisible by 3 and not by 5, then it's also not, and it's also not divisible by 2 because we add 2 every time. And this one is definitely not going to be even. Then we found the next one, and we continue doing that until we have 8 of them. I think that works. Let's print the result of this thing just to test it. Should just print this. Constant expression function never produces a constant expression. Non-constant expression constructor array cannot be used in constant expression. Happy now? No. Okay, I'm completely lost here. What's that one? 7, 11, 13, 17, 19, 23, 29, 31. That's that first row. Yay, we made it. Totally working. In other words, I was working on Sieve index 2 prime. And that should now work, I think. And we can test it by just printing a shitload of stuff for the Sieve index. One per line, one per line. Okay, int I equals 0, I is less than, but let's print 200 of them. That's a lot, 100 plus I, and then we print my function, or what is it, Sieve index I. God knows what this does. Make, it doesn't compile, of course. What is with less than less than? And still doesn't compile because undeclared identifier, Sieve index. I don't know, what did I do wrong here? I have a Sieve index here. This is what I want. Sieve index 2 prime. Yeah, that's the one that I wanted to test. And then we have to figure out if this is the same as the table. It's a bit hard to see, isn't it? How about I just copy it? How about I just format it? Because it's really hard to see. Can't type. I think half my brain is busy with thinking I should go eat it. I should go eat. Carlo, it's dinner time. It has been dinner time for an hour. And then I'm starting to make mistakes. Not really. No, not really at all. I have to increment I every time we use it here. Yeah, I think it works. It looks like the same thing. It is the same thing. So now we are capable of converting back from index to prime number. And what was the code here to begin with, right? Something like auto primes is the actual function that I wanted. Calculate primes. Just deleted code that I needed. And then I did auto prime from primes. And then we just printed that, I think. Let's print one per line. Oh, come on. Okay. So the sieve is filled with ones, therefore this is true, therefore we have an index. And then we can calculate a prime. And the prime was pushed back, and that was 7. And then we have to do the following thing. If, well, let's make it a do while loop. Maybe a while loop? No, a do while loop. While something continue, the something being that last prime is still less than the maximum, less than or equal. No. We calculate prime here, and then if prime is larger than the max value, then we want to stop. We're going to stop way sooner, but well. I don't know. I mean, a loop has to run until the square root of that thing or something like that. And then we do another loop, and then I have to break out of it at that point. So this is nonsensical, but okay. Yeah, maybe I should kind of make it 2 loops and then indeed break out of it when we reach the square root of the max value or something like that. Which then I have to calculate in advance. That's better. But No, I can do that much better. You can calculate the index in advance and then just run over the index of the whole sieve instead of this shit. So I do have to calculate the square root, but now I want to go the other way, going from the value to the index. I'll round it up or round it down? I think round it down, right? Round it down, okay. So the size is the index type. So the square root sieve index, just call it index, is, and then the other way. So that would be prime to sieve index. Square root. Is that a prime type? Theoretically. Although I'm also accepting other values here. See, it's an uint. Let's use the same thing here. If I have a prime, in this case it is actually the square root of that, so it's even much smaller. I could use int. It's not an offset, it just sorts the primes. Why did this work then? Better offset. Confused. Huh? How did this work when it's not correct? That's annoying. Oh, that's why. In the end, I did not need the offset. I just need the first row. Yep. I don't need offsets. But und then. I'll be very big. I'll have to be. Yeah, prime to Sieve index. Very annoying because of this one. So I can make a table that just converts this back. Column to first row. Yep, that means I need a second row. The first prime of the second row. Oh, no. Now I have to close those all by hand. Gotta be kidding me. I don't know how that happened. I think my keyboard must have shifted under the table so far that this button was pressed. Really strange things are happening. Okay, how do we calculate a const expression for the first, well, the prime whatever? I think it's the prime that is the next one in the, that we calculated here. It's next row, and then we skip it. No, it's much easier. Const. That's what it is. So I need an array, kind of like this one, but then that big, which we also have to initialize. Let me put that here. The thing returns, well, whatever, int. And the size is just that. And that is then prime to first row. First row prime to index. Where's to calculate? Calc first row. Put it above it. Okay, of course. No, I'm not, Roland. Just a Windows. Oops. Oop. I tried it once, but I really don't like. I didn't like it. It's confusing. Compression prime. What was this? Compression first prime second row. Yeah. Now, how are we going to do that in a lazy way? Yeah, it is an int. I don't know why I'm spelling ints in here. First row, why is it, the first row is just primes? Why is it not a prime type? Calc first row. I'm using first row. I'm using first row here. Could be any type. Let's use the prime. Let's put prime type. Well, they're not really primes. You know, it's like actually first row are those always primes? I don't think so. Probably not. Let's just keep it at int anyway. I mean, this table stores integers that are not divisible by any of the first 3 primes. But if you make this big enough, then I think it's going to contain non-primes as well. So I'll keep it as an int. And then here I have excuse me. I'm feeling sleepy. Expression. I'm gonna call it P anyway though. So maybe I should not call this prime then either. But yeah, I need a name for those integers. It's a very vague. Okay, run over all the numbers in the first row and then I need to know the column. Might as well run over all the columns then. Nah. I think I want columns. Column is the index here. Is that true? No. What? Let's call it column. Why am I feeling so confused? I think I should go eat. It's neither prime nor index. Very annoying. There's a Sieve index though. Yeah. Let's call this column or column. A column is also an index, but restricted to the first row. It's not a prime. Just remove it. Okay. Yeah, so I might as well run over all the columns, I think. So I know I have first row call, which then gives me the int here from whatever is in the first row. And then I want to do run from something to that. How should I call that something? N. I guess I could start at 2. No, it's not at 0. Do a while. Well, n is less than or equal. I wanted to round it down, so it is less than. And then we fill in that something is something. Plus in, I guess. Right. It is not right. What is wrong? This must be call -1, I think. So as soon as n reaches first row call, then we want to assign call to it. So go out of here, increment call. Same n, next call. So now this is true again, and then we assign the one higher call until again it gets to the next one. Yeah, this is correct. Let's print this array to see if it makes sense. Square root is not known. Everything is 0. It never ended, never stops either. What? Of course it should stop. It's a limited thing. Size is compression first prime second row, which is 37, I hope. Oh, it's calc. I meant, of course, it is 37. So then I run over this. Let's not do this. This should just print 37 values. And it does. Okay, so the -1 means you better not try that. And then the 7 is column 0 all the way up till 11 is the first one in column 1. Then we get 13. 17 is the next one, 19 is the next one, 23, 29, oops, 31. That should be 7. Why is 31 0 and not 7? because first row doesn't go that far. It should be the first prime of the second row. This one, we don't have that in the array. Oh well, let's just make it equal. And then we say if call is equal that, then we use that. Otherwise we use whatever. Equal this size here. No, it looks good. Now using this I can finally, hopefully, write this function here. Prime to Sieve index. So that's the inverse of this function. Sieve index to prime. So we take value. So value minus that is this. So you can get to the column to take the inverse of that. And I would have to just calculate that. That would be the first row to column. And then we can return the index is then simply row times compression repeat plus column. I'm not convinced. No, that's just print the results from 7 to 100. See what this gives. Call it P then, whatever. Not helpful because you just get a bunch of numbers. This worked, didn't it? Maybe we should check that as well. If it still works. Oh yeah, 7 and then 11 and then 17, 19, 23, 29, yep. And then this is the inverse. 7, 11. I'm already confused. Oh, this is the same thing. Waha. It's the same thing except this one stops here and the other one goes continues. Yeah, so 11, 13, 17, 19, 23, 29. And then everything started to fail. I think I'm forgetting to subtract 7. What is happening here? It looked so good till there. Definitely have to subtract the first prime first. First prime was first prime. Oh, no, I gave up. Well, it just didn't work. I was trying to come up with something that is faster, but I failed. So now I'm trying to just make something that is fast, but not necessarily a new method. This probably already exists. I just want to have something that generates prime numbers. fast, but not faster than humanity did until now. I kind of discovered that just my idea didn't really work, unfortunately. What is this? Row equals, yeah, so I track the first value and then we divide that and I get a row, and then we subtract it from the value. Of course I should subtract it from the value minus that in order to get a column. No, what the hell, man. No, so this way I get the first row, so that should be correct. And that should also be correct, so let's try this one. And now we have 11 is the next one, 13, 17, 19, 23, and 29, and 31. And 37. No, it works, I think. Yeah. 41, 43, 40. That's not a prime, but that's okay. This is not divisible by 2, 3, or 5. Yep. Okay, we got the inverse. Okay, so here I am pushing back. I already have the bloody index here. So we found the next prime, and now we have to zero values in the sieve. And I have to do that in several loops. So I start over. For int call is zero call less than something plus plus call. Okay, how many columns do we have again? That's the repeat. This one. Now for each column we have to calculate the first index that must be zeroed out. So that would be like the multiple index. Does the mod inverse accept negative values as well? Probably not. I think that the input has to be positive. But it is positive anyway, right? I need a modular inverse of we need a modular inverse of the compression primordial. Whereas the prime number is the modulo. And then I have to multiply that with the negative of the prime. No, the negative of the prime of the column in the column thing. So that would be the first row. The column. Where's my first row? This. First row and then cool. I don't want to do two modulos here. The problem is that this negative value here might be negative. Yeah, no, it's nonsense. I mean, I want to make it positive, so of course I could do something like modulo prime anyway. So I can do prime minus that, but that might still be negative. Or not. No, the prime is, yeah, that might still be negative. Say prime could be 7. First row column is of course going to be larger than that sometimes. So then what I really should do is, I don't know, maybe add a lot of primes to it. I'm afraid this prime is already going to be pretty big, so I don't want to multiply it with some ridiculously large thing like the second row prime. What do I have to multiply this with to make sure that it is larger? I mean, if prime is super large, then I don't have to multiply it at all. Jesus. Just for the small primes I have to do something. Oh, okay. Let's do it the way it works, and then maybe speed up later. It is so. Blah. That should work for now. And then I'll be nice and do a modulo prime before I multiply it. And then I'm afraid that even that can become larger again, so that's what I mean. Now I have to do another modulo prime. It doesn't feel particularly fast now, does it? Okay, my sieve. I'm so not convinced that this is correct. I don't think it works. We have no idea what it is doing, so let's run this in DB. So I've got to increment I. That would do it. I'm incrementing multiple index instead of I. But still, what the hell? If next prime, okay. Te. So max value is 100. That makes our sieve rows equal to 4. That's nothing. Which means makes the sieve size equal to 32. Set everything to 1. Can you print this? Probably not. It's all characters. Oh, 1 repeats 32 times. Square root. That's 10, of course. Square root index 0. Yeah, I guess that's actually correct. We only have to check if something is divisible by 7 and then we're done. Maybe 100 is a little bit small, but okay, it still hangs. Next prime is 1, of course, and then we have a sieve index, which is 0. Now my prime better be 7 then. Yes, and then we're done. Now prime is not larger than 10, so this is still pushed back. Now we're done. At least we're not done yet. We have to do this and then we're done. Call 0 calls less than compression repeat plus plus call multiple index. I guess that should be 0. And then prime is still 7. To do this until fill the whole sieve, starting at 0, stepping through it with 7. That's not correct. That should have been 7 times the primordial, compression primordial. But it should not even make a difference at the moment. So we do this a lot of times now. And then we go to the next column. No, yeah, maybe. So we're filling in a lot of zeros, too many zeros. Probably, and then all of those as well, so probably the whole sieve becomes 0. Is that the reason? Yeah. Mm-hmm. Now it finished. Okay, let's try 1000 because this was not enough. It's not working. Hmm. Hmm. Let's just use the table now I think about it, which is easier to check. So I want my largest prime to be 901. That's pretty close to 1,000 now I think about it, but okay. So then the number of rows should be 30. (901). The number of rows are going to be 30. Yep, and the total number of numbers that we have here, this total size of the sieve, is then going to be 8 times 30, obviously, which is 240. Push 3 first primes, and then we get the number of rows is 30. Yay! So that was 240. Make it valid. The square root of the max value is 30. Yes, of course. That's 901. And then the square root of that is about 30. And the index of 30 is, and now we can have a look at my table again, which is up here. So index of 30, that is, we don't have to go any further. 31 is already not interesting then. So 0, 1, 2, 3, 4, 5, 6. Do we see that correctly? Yeah, it is 6. Shy, I don't see where you see that, or you heard that, or anything. But no, it's not true. 10 plus 10 is 20. Probably not something I would have said, because I'm only talking about odd numbers. So I don't know what you are talking about. Oh, these are even. No, I didn't say anything. Okay, so the 6 is correct. What is the next thing? We start at sieve. We go to the end of the sieve and we check if the next number is set. Yes, of course, we just set everything. And then that index is, of course, going to be 0. And that should then, of course, return the first prime, which is 7. I need to have this in a different window, I think. So add a new window. New tab. For easy switching. So the first integer is the first entry in the table is 7. That's what we should get here. And still correct. And it is larger than the square root value, which was 30. No, if it is larger. Wait. If it's larger than break, so we don't break. We push it back. And then we calculate the step. Compression primordial times prime. And that should be 30, I think. No, much more. 7 of 210. And the reason that's 210 is because the first number that is divisible by 7 is going to be 7 plus 210, that correct? No, it's not. We're talking about indexes here. No, the index primordial is 30. No. Primordial is like factorial, but then with primes, so it's 2 times 3 times 5 in this case. Up till, but not including the 7. So if you add 30, I listed here on left to right and top to bottom. And then by doing so, you just get the next value here vertically every time exactly 30 larger than the one above that. So 7 plus 30 is 37, plus 30 is 67, plus 30 is 97, and here as well 11 plus 30 is 41, and so on. I'm confused about my step now. Step is supposed to be index step. So this is 0. 1, 2, 3, 4, 5, 6, 7, 8. I definitely want to stick into this column. I think I should have... oh, it's index. I should have multiplied it with the repeat. 7 times 8. So this is 8, 16, and then 7 down. 1, 2, 3, 4, 5, 6, 7. Yeah, this is divisible by 7, so that's correct. But this, the index of this in terms of the table is, of course, 7 times 8, because it's 8 wide. So that is a bug. Line 139. I don't know, man. I'll just keep debugging, I guess. Okay, where are we going to? Fill the sieve. Okay, am I going too fast now? Let's do it again. Fill it. I'm definitely going too fast. Now we were just at the start. The first prime. So the first prime was 7. The index of that is 0. And then it's not larger. Push the 7 back. The step now, here's where we were. The step should be 7 times 8. 56. We'll run over all the columns. And then we calculate the first index into the table. That is divisible by this prime in that column. So the first column, of course, should be 0. Because, well, this column is 7 is the first one that is divisible by 7. So this should be 0. And it was the last time, so I guess it's now again. And then we go down and we fill the whole table until Sieve size, which is still 30-ish. What was it? I can't find my keys anymore. 240. Yeah, sorry, 240. 30 times 8. What? Calculator. 30 times 8. 240. Oh, thank God. Well, it wasn't. So we go down here and then 1, 2, 3, 4, 5, 6, 7, and that's 217. So then we're going to fill that frame. So I is 0, that's a 7. Fill it with a 0, why not? And then fill I is 56. Is there a way to get my prime number back here so I can see that that is indeed that? I think that's print Sieve index to prime, if I'm not mistaken. 217. Yeah, and 217 is divisible by the prime, of course. Great. And then the next one is 427, which is also divisible by 7. I can even see that myself. Next. And now we're done. Or not. Wait. I think the next, we still have a next one, right? 637. We even have a next one, I think. 847. Yep, that was the last one. Now we go to the next column. Now it's a drum ruffle, because if this difficult line works, the multiple index is 5, which means that we're now saying 23 is divisible by this is not working. What went wrong here? I should have found the first thing in this column that is divisible by 7, which is this one? No. This one. Twenty-three is the result of dividing this by 7. The 5 I also saw. I think the 5 here is literally the column, so I forgot to multiply that with compression repeat as well, because that makes the index here the current the column plus the repeat times 5. I don't have the index at all here. The step is correct. I have to multiply that one as well with the compression repeat. And then at least we would have started at 40. And even that is not correct. And then I have to add call to it. So call is 1. So what I really should have done is print call plus the compression repeat times the value that was returned here, 41. Then we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 16, 24, 32, 40, 41. Pew. Yeah. And now we go down with the step again. 1, 2, 3, 4, 5, 6, 7. That is also divisible by 7. I think we are getting closer. Yes. 143-ish, yeah. 143, yeah. That should have been call plus the compression repeat times multiple index. Calculate primes, run, next, break 142, continue, next, so now it's 5, and then I starts at 41, which belongs to 161. Yep, that's that one. And then the next one is 1, 2, 3, 4, 5, 6, 7, 371. Oh, I skipped it. Well, whatever. So now we have multiple index is 4. Let's just go for it. That prime is 133. Which is divisible by 7 apparently. Doesn't look like divisible by 7 at all. I don't know. 1, 2, 3 divided by 7. It is 19. No. Yeah, indeed. If you subtract 70, then you get 63. No, I think it works. So continue, continue, delete all breakpoints. Continue. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. That's all nice and dandy, but now I want to see this work for something larger. Why is it stopping at 947? Oh, because it doesn't go further than the square root. Okay, so 947, and the next prime after 947 is probably larger than the square root of the thing. 947. What did I type in? So 947 times 947 is pretty damn close to this number. So we have to continue the loop. After this, just the sieve has been filled. So let's see, how do we continue the next prime? I think the same thing, just this. Except that I don't want to do this test really, but that means that we go over it. Extra test per, yeah, nah. As if that isn't slow. Okay, let's forget slow. I'm going to do that, and this is no longer necessary. Yep, so whoop. And then here we have, of course, that. Well, that were all the prime numbers until 1 million, or let's make it 1 million. Let's make it 10 million. 10, is it 10 million? Yes, 10 million. So let's all prime numbers up till 10 million. That's that. And then I can, it did start at, see, just write it here. It did start at 2, I hope. Okay, it starts at 2, and then that's the last one. So now I can see that we see lines troop. So there's that number of primes we have now. It's less than 1 million of primes, not that much. Let's see if it's correct. Largest prime. Yep. The 664,579th prime is 9999991. So it works. Cool. Now I have to do boring stuff like speed it up, because it's can definitely be made faster, I think. Let me print a little bit less than all the primes. Let's just print the prime size prime is primes are begin. Well, no, back. Using compressed Eratosthenes, Kali. You know, with the modular inverse in it. Somehow I doubt that. 1, 2, 3, 1, 2, 3. Oh, it fits. So how large can we go? Okay, let's see if this is correct cell. I mean, to test overflow-ish, this stuff. Alt tab. Submit. Yeah, that looks lots of 937. So that's correct. Oh, that's horrible. Oh, golly, I did the Sieve of Eratosthenes, and I invented it myself when I was 12, without having a computer or anyone who taught me anything. I got a book with basic language, programming language in it, and then I wrote that program. It was my first program. I think this is already considerably faster than the Sieve without compression. Kind of must say I had not expected it to be this fast for that many primes. 50 million. in 3 seconds. Let's compile with optimization. Does it compile with optimization? No, no optimization inside. How do I do that? PEVI. Release. No, just release, I guess. Now we get all kinds of errors. Unknown type. Oh, interesting. It gets dragged in by my debug, I guess. See standard int. No. Yeah, I didn't want to boast that like that, but you said we had to do this in school. I read it as middle school, or maybe now high school, I guess. You said computer science even, but I read it as what is the word in English? Degrading, say, like as if you meant it like Jesus, what you're doing is so simple. We already did that in high school. So then I basically said that what you are referring to that you did in school is what I already did when I was 12. So this is more difficult. And then there's always a difference between inventing it yourself and just typing in something that someone else taught you. I think there's also a pretty big difference. I kind of invented this myself now, but I'm convinced it already exists. I already encountered the word compressed Eratosthenes when looking up integers in the online encyclopedia of integer database. The word popped up, so it must exist. And I forgot to include the vector as well. Well, and memset, which is defined in string, I think, which is really weird. Well, C string then. Is that true? Building. Now, let's run this again. Still slow. Well, slow. It's not really fast at all. It went from 3 points so many seconds to 2 points so many seconds. Yeah, 2/3. we can get this below 1 second, then I'm pretty happy. Let's try to do that. Or at the very least, look at what I thought was annoying that I had to do that. So this is the loop where we fill in the sieve, right? And then we fill the sieve until we reach the square root here, and then we just read out everything else. Now, of course, this is going to be pretty damn slow because it's going to be a lot of primes. And a push back to a vector. Can we not do that? I bet most CPUs like wasted on this point. But the one speed up that we can definitely do is figure out how many primes we expect in advance, and then make sure that the vector is big enough from the beginning, so it doesn't have to be moved a lot of times. So I want to have a certain upper bound for the number of primes, sorry, lower bound for the number of primes. Which is more or less the, I think, well, the logarithm of the maximum value. But that is more or less, so I want to be sure. So let's ask ChatGPT, it might even know it. What is a good... I'm starting with approximation, and then I'll make it an upper bound or a lower bound. Approximation of the number of primes below a given integer n. Wolfram? Dude. I don't think... Oh, it's just passing it literally to Wolfram. Maybe Wolfram Alpha does know it, but... I'm asking for it. It's weird. I'm asking for approximation. Right, so n divided by the logarithm of n, okay. But now I want to have an... Let's say it is 146. Then I want to have 147 or 108. Is that an upper or a lower bound? I think lower bound. I'm not even sure, dude. What the hell? Okay, dan I guess I meant upper bound. Because border, no. Hmm. And then we have to take into account that ChatGPT might just dreaming things up. But it is good to get all the keywords. So I'm going to Google for Rosser's theorem. Prime upper bound, comma, Rosser's. You gotta be kidding me. I get what? Copy. Bounds for the myth of no prime formula, no. But bound for prime product on the Riemann. Ooh, that's much more accurate, I think. But might be a bit overreach here. Explicit bound on the number of primes of given size. Ross's theorem. Turn on dark mode. Well, this one is good enough then, already, I guess. Can I blow this up? So number of, no wait, what is speed? Nth prime is less than this. Yeah, you have to calculate it. Do they not inverse this already? You just scroll to the bottom because well, maybe it's me, but I thought they were. Just look at the title. Oh, this is literally the nth prime number. Yeah, that's not what I wanted. Damn it. Okay, let's have a look here. It's by n that we need, but then as upper bound. No, at least I'll have some. Whatever here in the table. So it seems that the x divided by log x is always smaller than the actual value, because these are all positive. And lie x is larger, because this is all positive. And even a pretty damn accurate as well. Very accurate. So I think I want to have the lie x. What is lie x? Doesn't say. What is li? Did I close that page? Damn it. Yeah. Are we willing to spend a whole second on calculating the size? Or is this just this site that is the reason that's so slow? Count in n is 1000. Yeah, just a loop of 1000. So it shouldn't be taking that much time. I cannot imagine that this cannot be done faster, however. Is this now what I want or not? I log B. Integral log. And the B nobody knows. I'm going to eat and then I'm going to watch this YouTube, which I probably cannot do on the stream. So I'll be back later, guys.